Hello, my name is Edsko De Vries, and I am one of the engineers on the Ouroboros consensus layer. And today I want to talk to you about how we do the migration from Byron to Shelley and beyond. Now, as you are all aware, a blockchain, despite the name, isn't actually a blockchain as such. There are occasional forks in the chain. And when these forks happen, one of the responsibilities of the consensus algorithm is to choose the right fork. This is one of the main responsibilities of a consensus algorithm. Now, however, when we talk about a hard fork, we actually usually mean something different. Now, here's the definition from the Investopedia, and that says a hard fork, as it relates to blockchain technology, is a radical change to a network's protocol that makes previously invalid blocks and transactions valid, or vice versa. A hard fork requires all nodes or users to upgrade to the latest version of the protocol software. That is, in fact, not how we are going to do the hard fork from Byron to Shelley and beyond. The first part of this slide, the first part of this sentence does not apply. A way that they define a hard fork is that we have some chain, right, possibly with forks in there, and then everybody stops, and we do some sort of translation, and maybe we update the software, maybe we translate the blocks, maybe we add some new transaction types, maybe we remove some transaction types, doesn't matter, and then we restart again. We don't want that sort of discontinuity in the chain. Instead, what we're going to do is we're going to have the chain as it is at the moment, our Byron chain, and that Byron chain can be extended with Shelley blocks. We're going to have a mixed chain. And it is the responsibility of the hard fork combinator that I'm going to talk about and that I've been developing over the last while that makes this possible, that takes various different kinds of ledgers and makes them look like they are a single chain. And there's no single point where we say, okay, now we have done the hard fork. We really have a mixed chain. For example, suppose that we have the situation on the screen right now where the longest chain ends in a Shelley block. If at some point we discover a longer chain that we prefer, which is still in Byron, well, then we switch to it. We go all the way back from Shelley, back across the transition point to a Byron block, and we go forward again. Now, this is limited by the maximum rollback, so just like any rollback, but it just behaves like a normal chain. It just happens to be a chain with multiple kinds of blocks. So the way that we do the hard fork is actually rather different from how many blockchains do it. And so the rest of this presentation, I want to talk to you about how we do this and what makes this possible. Now, in order for me to explain this to you, I need to explain a little bit about how the consensus layer works. Now, the heart of the consensus layer is the chain database. The chain database is a specialized database that stores blocks and does chain selection, amongst other things. So the API to the chain database is very simple. We have a way to add blocks and we have a way to get blocks. There are no API calls for switching to a fork. There are no API calls for rolling back, nothing like that. Instead, all you do is add blocks. And the chain database itself is responsible for deciding, do I want to adopt this block? Maybe this is the final block that I needed to switch to a longer chain, etc. It makes those decisions internally. So we get blocks from our upstream peers. They get added to the chain database. And our downstream peers, they can request those blocks from our chain database and read them. Now, of course, for those downstream peers to be able to know which blocks to request, they need to know what our chain is. And so they run a protocol that we call the chain sync protocol. The chain sync protocol is a protocol that informs you and tells you how our chain is evolving. It might say, oh, we adopted this block. We had added this block to the end of our chain. Or it might say, oh, you know what? We rolled back a few blocks because we were switching to a fork. So we rolled back a little bit and then we're applying some other blocks. And so in order to make this available to our downstream peers, the chain database offers a cursor, which which internally we're calling a reader. And that cursor is precisely this. It's the chain database informing you, add block, roll back, add some more blocks, and so forth. And this is then made available to our downstream peers. Now, this information is not done in terms of blocks, but rather in terms of headers. And the reason for that is that it's more efficient, right? Downstream peers will be following lots of chains. They might not want all those chains. They might only want one of them. And so we can send them headers. They are small. And so once they make a decision which chain they want, they can then request the blocks from that chain rather than getting blocks from all of them. Now, and of course, we need to do the same. So we are tracking our upstream peers. We are tracking their chain in terms of headers. We do chain selection on them. We look at those chains and say, okay, this is the one we prefer. We then validate those headers, and that then feeds back into the block download logic. So we say, okay, this is the chain we want. We validated the headers. The headers are okay. So please go and download those blocks now. And then those blocks get added to the chain database, and they might get added to our own chain. Now, of course, in order to validate headers, we need to have the chain state available. For example, in Shelley, your right to produce a block depends on your stake. Now, your stake, it depends on the ledger state, right? It depends on all the transactions that have come before. So the chain database offers an API that says, please give me the ledger state corresponding to our current chain. And that is the ledger state that we then pass to validation in order to validate headers. Now, that same ledger state is also used for many other things. For example, when we get transactions from our downstream peers, this is the opposite order here. So we get transactions from our downstream peers. We need to validate those transactions. Of course, validation of a transaction also is with respect to a particular state of the ledger, right? The transaction is valid or invalid with respect to the transaction that came before. So when we validate a transaction, we again need that same ledger state. Once they are found that to be valid, we add it to the mempool, and then our upstream peers can request those transactions from us. And of course, if we have the right to produce blocks, then when we can produce a block, when we have the right to produce a block, we sample the mempool, get a bunch of transactions from it, and then make a block that contains those transactions. That block gets added back into the chain database, which treats it just like any other block and adds it to the chain if appropriate. And finally, we also have an API known as the local state query protocol that allows tooling such as the wallet to query the node about the state of the ledger. So for example, in Shelley, it might ask for the stake distribution. So it's important to realize that all of these components behave differently depending on which ledger we are running, right? If we are running a Byron ledger, then the chain database is storing Byron blocks and it's doing Byron chain selection. Chain selection is different in Byron and in Shelley. For example, in Shelley, we look at keys. And if we have two chains of the same length, but the tip of one is signed by a newer version of the same key, we prefer it. This doesn't happen in Byron. And so chain selection is different. And of course, blocks themselves are different. Like I said, if this is a Shelley chain, then we need to do Shelley chain selection. When we are doing headers, here we're doing the same thing, right? Just like we do within the chain database, except here we're doing it on headers. Same thing. If this is a Byron chain, then we're doing Byron chain selection. If this is a Shelley chain, we're doing Shelley chain selection. When we validate headers, validation of headers is different in Byron and Shelley. In Byron, it depends on the Byron delegation state, for example. In Shelley, your right to sign a block or not, it depends on your stake, and so we need to know the ledger state. But these are completely different rules. And so if this is a Byron or a Shelley state, the validation of headers is also different. The queries that we support are different. In Shelley, we might want to ask for staking information, and in Byron, that simply doesn't apply, right? So the wallet is able to submit different sorts of queries if it's a Byron chain or a Shelley chain. The mempool behaves differently. Transactions in Byron are different than transactions in Shelley. They have different rules, different errors. The transactions themselves look different. And so, yeah, if this is a Shelley chain, they have different transactions. And of course, block production is also different, right? If this is a Byron chain, we're producing Byron blocks. If it's a Shelley chain, we're producing Byron blocks. So every component of the chain of this consensus layer is different, behaves differently for different ledgers, whether this is a Byron one or a Shelley one. Now, the way we achieve this is actually by making sure that the consensus layer doesn't know anything about these individual ledgers. The consensus layer is quite a big piece of software, but it's very abstract. It doesn't know any specifics about any specific ledger. And that is very important because that means that the same consensus layer can be used for many ledgers. Right now, the Cardano mainnet is running Byron, and it's running the exact same consensus layer that the Cardano testnet is running, which is running Shelley. Right? The consensus layer is exactly the same between those two, no difference whatsoever. So how do we achieve this? And I don't want to talk too much about this in too much detail, but the key idea is that we have all kinds of abstractions that tell the consensus layer what kind of properties that we're expecting from the underlying ledgers that they should satisfy without pinning it down to a specific concrete ledger. So here's just an example. A ledger must have at least these two classes, instances for these two classes. So we must say, so we say L is a ledger if we must have some sort of error associated with this ledger, right? The kind of errors that we can get when applying blocks. And we must be able to tick the ledger state. Ticking here means that ticking of the clock. So how does the ledger state evolve? Simply by the clock ticking. So we're not yet applying a block, but just the clock ticks. And for example, in Shelley, at some point, we switch which state distribution is the relevant one for determining who's the leader. And that's based not on which blocks come in, but simply has the clock reached a particular slot. And so that's ticking of the ledger state. And then we also need to be able to apply a block, of course, to a ledger. So we have some sort of ledger state and a block. And then we must be able to take this block, apply it to the ledger state, and what we get back is either the updated ledger state, or if the block was invalid, some ledger-specific error message. And then in addition to these two things, we also need some sort of ledger config. So all of these ledgers need some static information. For example, how much rollback we support, how long is an epoch, that sort of thing. So that's the ledger config. And so we have lots of abstractions like this that allow us to describe what we request, what we require from a ledger without requiring a very specific ledger. But that still doesn't help with a mixed chain, right? So far, I've been talking about a pure Byron one or a pure Shelley one. I haven't yet described how we can do a chain that has some Byron blocks and some Shelley blocks. And this is where the hard fork combinator comes in. So the hard fork combinator defines a new type of block called hard fork block, which is the composition of lots of other blocks. So for example, the Cardano block will be a hard fork block of a Byron block and a Shelley block. Now, what that means is that we are currently running Byron. At some point, there will be a transition to Shelley, and then the whole thing smoothly transitions to be a Shelley chain. Now, more than that, it's entirely possible that we on our chain haven't done that transition yet. And so we are running Byron, but some of our upstream nodes already have done a transition. And so they are running Shelley. This is entirely possible. And the hard fork combinator makes all that possible. Indeed, it might be that some of our upstream nodes have already transitioned, so they are already in Shelley, and some have not. So we might have a mixed bag there where we're doing chain selection between some chains that are Byron and some chains that are Shelley. And also that is not a problem. And moreover, this hard fork combinator doesn't care that it's only 2 errors. We could have any number of errors. So if we are ready to transition to Goguen, we just add one more list entry into this list and nothing else needs to change. The hard fork combinator itself does not need to change whatsoever. And now, simply by adding this one more block here, we can switch from Byron to Shelley to Goguen and beyond. So, in order to make that work, there's a lot of details that we have to get right. And I only want to talk about a few of them in this presentation. And the first thing that we need to talk about is types. The Byron world is completely different from the Shelley world. They have its own type of ledger, its own type of blocks, its own type of transaction, its own type of errors. They are all totally different from the ones in Shelley, which will be different from the ones in Goguen, different from the ones in Basho. So we need to be able to deal with all these different types. So I'm going to talk, there's basically three ingredients that we're going to need: n-ray products, n-ray sums, and telescopes. Now, what are those things? First of all, I mentioned to you that we need config, right? Some static information that every ledger needs to operate. Now, if we're running lots of ledgers, then it makes sense that we're going to need a config for all of them. And so this is called an n-ray product. So this NP here is n-ray product, and so we need an n-ray product. This access parameter here is the blocks that we have. So think of access as Byron, Shelley, Goguen, whatever. So NP block config of access means that for every element in access, so for Byron, for Shelley, whatever, we're going to need a block config. So if we set Cardano block to be equal to hard fork block of Byron block, then this is just equivalent in brackets. So this is the thing in brackets is just equivalent to the thing above it of just a Byron config. If we set Cardano block to be Byron block, Shelley block, then it's equivalent to having both of those, 2 configs. If we add Gauguin in the list, then it's equivalent to having a triple, right? A config for Byron, Shelley, and Gauguin. Now, that's an NP. A header in this context is a header from one of the eras, right? A config was a config from all of the eras. A header is a config from one of the eras. So I think we call this an N-ray sum. And again, if we just set Cardano block to be equal to hard fork block of Byron block, then a header must be, since we only have one era, a header from Byron. But when we add Shelley into the mix, it's a header from either Byron or Shelley. When we add Gauguin into the mix, it's a header from Byron, Shelley, or Gauguin. And so this extends very smoothly to any number of eras. Now, this N-ray product and N-ray sum come from a paper that I wrote together with a colleague called Anders Leu. And so rather than spending too much time on that, I want to spend time on something that we developed specifically for the hard fork combinator, which is a telescope. And the telescope we use for the state of the ledger. So the state of the ledger in the context of the hard fork combinator is a telescope of a past ledger state and a current ledger state. Now, what does that mean? If we are currently in Byron, then the hard fork state, the state of the ledger in this context, must necessarily be the Byron state, right? The current Byron state. However, if we add Shelley into the mix, now there are two possibilities. Either we're still in Byron, in which case we have a current Byron state, or we have transitioned, in which case we have a current Shelley state and we have a past Byron state. Now, when we add Gauguin into the mix, we still have those two possibilities, but we also have the possibility that we have a current Gauguin state and a past Byron state and a past Shelley state. So I call this a telescope because it's kind of reminiscent of this old style telescope that we can extend segment by segment. All right, every time that we transition to the next era, we are extending the telescope one more bit. And so here's the definition of a telescope. A telescope, we can always construct a telescope that only has one segment, and so we just need a current state. So think of F as being a current ledger state and G as a past ledger state. And moreover, if we want to extend the telescope, well, then we just need a past state, say a past Byron state, and then the remainder of the telescope. So that's these two constructors here. Now, these telescopes come with quite an extensive API, and I want to talk just about three of them. And the first one is extending. So extending means that we're going to make the telescope longer. We're going to extend it by one segment or more. Now, this type signature here looks a bit complicated, so let's take this bit by bit. So it's going to be a function from a telescope to a telescope, right? We're extending the telescope, so that makes sense. Now, suppose I have some telescope here where we have, so think again as G as being past and F as being current. So we have a bunch of past states and then a current state. Now, what we're going to do is we're going to look for the tip of this telescope and check, do we need to extend it, right? Are we ready to go to the next era? So in Byron, if the tip would be in Byron, that would mean have all the votes come in to go to Shelley, have they been endorsed, etc. And for Shelley, it's a similar process, but not quite the same, slightly different. So we're going to look at this tip and check, should we extend it? Should we go to the next era? Now, since we don't know where the tip is, since we don't know where the state of the system is, we need such a function for every era, right? We need such a function from Byron, for Shelley, for Gauguin, whatever, and then we look which era are we in and we pick the right function. Now, if we are in this era, then if we do decide to extend it, we need to take the current Byron state, say, and turn it into a past Byron state and a current Shelley state, right? We need to extend it by one. So this is this extend type. Now, after extension, it's possible in principle that we might have to extend again immediately. And so we need this sort of function to extend up to the end. Now, and moreover, since we don't know where the current tip is, we need such a function for every pair of eras. So that's this in pairs of extend, right? For every pairs of eras, we need a function that extends from the previous one to the next one. Now, similarly, retraction works very similar, but it's sort of the other way around. So where extension was making the telescope longer, retraction is going to make the telescope shorter. And again, let's take this step by step. So we have some telescope again. We're going to look at every past era in turn. And we're going to check, should we retract to this era? And retraction, by the way, the intuition here is that we roll back, right? When we're rolling back to switch to a fork, we have to retract the state and then move forward again. So, okay, so we look for the era that we need to retract to. If it's not the first one, And again, the function that we use is again different for every state. So we have a function that checks, should we retract to this state? If not, well, then we look at the next one and the next one. And so again, for every era, we need a function that checks, should we retract to this era? Now, once we found the one that we want to retract to, then we need a function from the current tip of the telescope, the current era, back to this past era. Now, since we don't know where the current tip is, we need such a function from all possible future eras. And since we don't know which era we're retracting to, we need such a bundle for every era. Right? And so this is this tails thing. So for every pairs of eras, a retraction function from the future one to the past one. And then finally, alignment of telescopes means that if I have two telescopes, where one might be shorter or longer than the other one, we can now align them, right? So we can take the other telescope. If the other telescope is shorter, we extend it. If the other telescope is longer, we retract it. Once they are aligned, we can then have two current states that are both at the same type now, the same era, and so we can apply a function on both of them. And that function would have the same type. So that's alignment. Okay, so then the only thing I haven't yet told you is what current and past means. I've been talking about current ledger state and past ledger state. So what does current and past mean? Well, a current ledger state is simply a ledger state along with some bound on this era. And the bound tells you when this era started. And for past ledger states, a past ledger state is two bounds. When did the era start? When did it end? And a snapshot. And a snapshot is simply a snapshot of the most recent like sort of the final ledger state in that era, or it's GC'd, right? That snapshot could be nothing, basically. If we are sure that we're not going to need this past snapshot anymore, if we are sure that this is now so far ahead that we can't roll back so far anymore that we're going to need this past snapshot. Okay, and that leads nicely onto time, right? I said bounds. When did the era start? When did it finish? Well, that means we're talking about time now. So, in the Ouroboros family of consensus algorithms, time is divided into slots. Right? In Byron, a slot is 20 seconds, and we have a block produced every slot. In Shelley, a slot is only 1 second, and we expect to produce a block maybe every 1 in 20 slots on average. Similarly, slots are divided into epochs. In Byron, an epoch is 21,000 something 600 slots. And in Shelley, it's going to be more than that. The exact number doesn't really matter. But that means if I then have some time t, a wall clock time, right, a normal clock time t, and I want to know which slot is this, the conversion is a little bit tricky. So let's just see in a simple example. Suppose that in Byron, just for the sake of the argument, in Byron we have 10 slots per epoch, and in Shelley we have 16, say. So in this example here, we can see that this time t here within the Shelley part of the chain is in epoch 1, right, the second epoch, and relative slot 14, which makes it slot 30 within the Shelley era, which means that since we had 3 Byron epochs as well, it will be overall epoch 4 and slot 60. Okay, simple enough. However, if the transition from Byron to Shelley happened 1 epoch later, and we take that exact same time t, then this now becomes, actually it happens to be still epoch 1 within the Shelley era, but now relative slot 1, which makes it slot 17 within the Shelley era, which means that overall it's now epoch 5 rather than 4, and slot 57 rather than 60. Right? So the exact same clock time t has a different translation from slot to slot and epoch, depending on when the transition happens. Now here's the thing, that transition, when the transition happens, is decided on the blockchain itself, right? In Byron, we're going to vote. Okay, are we ready to transition to Shelley now? Yes, we are. Okay, collect the votes, endorse the votes, etc. Once that is all done, we then transition. So this decision happens on the blockchain. So that leads to the inevitable conclusion that if our ledger state is far behind the wall clock time, and we ask, okay, which slot is this time t here? We have to say, we don't know. Right? If we don't know when a transition to Shelley is going to happen yet, we might not be able to do translations for this slot t. Now that's a problem. And in order to make that problem slightly more tractable, we introduced the concept of a safe zone. Now, a safe zone is an area of the chain such that if we don't yet know when a transition will happen, we are guaranteed that that transition will not happen within that safe zone. So that means I can do time translations for any period, for any time within that safe zone, even though it's ahead of our ledger, because I am guaranteed there won't be a transition there. And so the information I have about slot length and epoch size for my current era and any past eras is sufficient to do any translations that I might need. We still have to be careful. So one of the things, for example, that the chain database needs to do is when a block comes in, if that block was produced prematurely, right, is actually a block from the future, then we should not yet adopt it. But a block doesn't have a timestamp. A block just has a slot number. So if a block comes in with a slot number, suppose here around time t prime here, I then need to somehow compare that to the wall clock time t. But if the wall clock is well ahead of our ledger, I can't translate the wall clock t to a slot number because I don't know when the transition has happened. However, I can take the slot number of the block and translate it to a wall clock time, normal clock time, because that is within the safe zone or even before the safe zone, and so that's okay. So we cannot take the wall clock, translate to a slot, but instead what we can do is take the slot of the block and translate to a wall clock and then compare. So we have to be a little bit careful in how we do things. Now, in order to make predictions about the future, it's not necessarily the case that that there can't be any changes. The only requirement is that if there are changes going to happen, we know what they are. If we know what they are and when they will happen, well, then we can do time translations, right? So we need to make a distinction between the safe zone, which is the zone in which we are guaranteed there will be no transitions, provided that we don't know yet when the transition will happen, and the forecast range, which is the range in which we can do predictions. If we don't yet know when a transition will happen, those two things are the same. However, if we do know when a transition is going to happen, so for example, we're still in Byron, but the voting has come in and we know when we're going to transition to Shelley, at this point, the safe zone of the Byron era no longer is important. Our forecast range will extend up until the point that we transition to Shelley, and then to the safe zone within Shelley. So now our forecast range is now up to the transition point and then the safe zone of the next era. Now, why is it important that we need to look ahead? Well, I told you that we are doing validation of headers, right? We're tracking our upstream peers, we're looking at the chains, and we're doing chain selection and validation, but not on full blocks, but on headers. Now, of course, if I only have a header, I cannot update the ledger state, right? I don't know how the UTXO evolves, for example. So I must be able to use the ledger state corresponding to my current chain in order to validate headers which are ahead of my current chain. And so this is why it's really important that we can look ahead. And so we then need a lemma that says if my current tip is at point T here, and a header H comes in, and which is potentially on a different fork, right? And so we have a common ancestor A between T and H. The lemma says that we can use the ledger state at T to do time conversions for H. And I won't show you the full proof, but the intuition is not so difficult. Since H is within the forecast range of the common ancestor A, all changes that will happen within this forecast range are already known at point A. Moreover, as the chain grows, we might learn more information about how the chain evolves and how these time conversions evolve, but the information that we learn will never invalidate all the information. It's monotone. So since the information at A is sufficient to look at H, since all changes are already known, and since T comes after A, the information at T must also be sufficient. And for this, it doesn't really matter whether T is inside or outside this forecast range. The only important part is that H is within this forecast range. Now, if H is outside of this forecast range, we cannot do this, right? Now it's possible that there is a transitioning happening, right, before H, but after the forecast range, that T does not know about. And so if we try to use information at point T to conclude anything about H, we might get incorrect answers. Now that it means that we actually have a condition on the underlying ledger. Suppose that I told you, well, actually I didn't tell you that yet. In consensus, the maximum rollback is limited. And it's called a security parameter, and we usually denote it by K. So once a block is deeper than K blocks into the chain, you are absolutely 100% guaranteed that will never be rolled back. We will never switch to a different fork that doesn't include that block. So that means that when we have validated a header, the common ancestor must at most be K blocks deep into the chain. It can't be deeper. But now suppose that this is the case. We can only evaluate up to the forecast range number of headers from that point K. Now, chain selection in Ouroboros is usually based on chain length, maybe some additional parameters, but chain length is the most important one. So if I'm going to explore a different chain, that's only useful if I might switch to it. I can switch to it if it's longer than my current chain. But that means that I must be able to evaluate enough of that other chain for it to get longer than my own. So that means that we have a condition on the ledger that says that the safe zone, which is determined by the ledger, properties of the ledger, must at least be K. Otherwise, we might get into a situation that we have rollback K blocks, but then we can't evaluate a sufficient number of headers to get a chain that's potentially longer than our own. And if it's not longer, we'll never adopt it, and so there's no point even looking at it. But actually, that's not the only condition that we impose on the ledger. We have a second one as well. So I told you that if we don't yet know when a transition happens, the safe zone equals the forecast range. And we also said that if we do know when a transition happens, the forecast range extends to the transition and then includes the safe zone of the next era. But it's entirely possible that the safe zone of the next era is much shorter than the safe zone of our current era. Right? And these are properties of the ledger. There's nothing that combines these. And so if we're not careful, we might end up in a situation where we don't yet know when the transition is going to happen. And so we apply the safe zone of this era, and we might have some time t that fits in with the safe zone. Now, in the very next slot, we now learn when a transition will happen. And so now our forecast range is up to the transition point, and then the safe zone of the next era, which could be very short. Now, if this happens, we might have made a decision about time t that is actually incorrect, because time t falls outside the safe zone of the next era, right? So it's past the transition point. We didn't know that. We made some conclusions about it, assuming that there was no transition, and so we derived the wrong answer. And so there's an additional requirement on the underlying ledger that says that the moment that you learn about the transition point, at that point, there must still be a final safe zone before the transition happens. So when we go from not knowing transition point to knowing the transition point, there must still be that same buffer of slots before we can transition to the next era. And if that is the case, then this problem can't happen. So I've talked about two aspects of the hard fork combinator. I've talked about how we deal with all the types, and I've talked about that we need to be able to look ahead, and because we need to do time translations, and these time translations depend on when transitions happen, and so the hard fork combinator needs to be very, very careful in quite how far we can look ahead, how much information do we know about time, how much information do we not know about time, what kind of conditions do we have on the underlying ledgers to make all this possible. But this is to do with the assumptions about time within the consensus layer itself. The ledgers also think about time. For example, in Shelley, rewards happen at epoch boundaries. But when do epoch boundaries happen? Well, that depends on when the transition happens, right? If we look from all we have is a slot, if I want to know, is this slot an epoch boundary? Well, that depends on exactly when the transition from Byron to Shelley happened. And so there's this abstraction called epoch info, which is this translation between epochs and slots. So for example, I can go from this function called epoch info epoch that takes a slot number and gives you back the epoch number. Now, this is all in some monad M, and the reason for that is that as the chain grows, we learn more information, and so we might give you have more information about these translations, right? If we ask for a slot far into the future and ask which epoch is this, we might say, we don't know. As the chain grows, we learn more information, and so the behavior of this function changes. However, in the Shelley ledger, we find this. Globals here is a type in the Shelley ledger, is basically the configuration required by the Shelley ledger, and we see epoch info of identity here. which basically means that Shelley is insisting that this epoch info is static. It can't change. And indeed, if we're running a Shelley net by itself with no transitions from Byron to Shelley or to somewhere else, that's perfectly fine, right? There is only one epoch size and one slot length, and so this is okay. So the Shelley ledger itself has the illusion that it's the only ledger in town. But of course, when we apply the hard fork combinator to this, that's not the case. So how do we reconcile these two things? Well, I told you that the hard fork combinator contains the config of every era. But that was a little bit imprecise. So what I should have said is this. The hard fork ledger config is not a ledger config of every era, but a partial ledger config. Now, what is a partial ledger config? It's a ledger config minus the epoch info, minus time information. And so we must be able to construct a ledger config from a partial one if we know the epoch info. Now, this epoch info that we're going to provide to this complete ledger info is an epoch info, which is a snapshot of the current state of the chain. Remember that I said to you that these telescopes contain past and current ledger states, and we had these bounds in there. Now, the reason for these bounds is precisely so that we know exactly when the transitions between eras happened, which means that we can take this, the ledger state, look at it, and construct an epoch info, which is a snapshot of the current state. If you try to use this epoch info for a slot very far into the future, you get an exception saying past horizon, right? We don't know anything about this slot. But if you don't look ahead too far, then you can use this epoch info to do time translations. So that means that the individual ledgers can have the illusion that they are the only one in town, right? They have an epoch info identity. They don't need to worry about the fact that actually this epoch info changes. Instead, the hard fork combinator takes care of this. It records partial ledger configs. And every time that we call one of the underlying ledger functions that requires the full config, at that point, we look at the ledger state, take a snapshot of it, compute an epoch info for it, and then pass that epoch info, which is now an updated epoch info, temporarily, to the ledger function, make it do what it wants to do, and then we move on. Never ever storing this epoch info, right? Because the epoch info is ever changing. And so that's really all I wanted to talk to you about. So in all of this, abstraction is absolutely key, right? So, software which is quite so abstract as the consensus layer is not to everybody's taste or everybody's ability. However, it is very, very important in order to achieve something like this, because without abstraction, we might accidentally take advantage of specific properties of the ledger that simply don't hold, right? Whereas if we are very abstract, then we must write down, we must think very carefully about, okay, what is the requirement? What are the requirements on the underlying ledgers that we have? What kind of properties do we need from them? And then once we design that, then we can then have the exact same consensus layer work for Byron, for Shelley, for Gauguin, and so forth. Moreover, since it's completely abstract, we can then define something like the hard fork combinator, which no matter how many eras we have, and no matter what those ledgers are, as long as they have certain properties that we think about because it's all abstract, we can define this combinator, this piece of software that takes any of these ledgers and just makes them look as if it's a single chain. There is no hard fork at all. Right? So in computer science, this sort of compositionality is very important. We want to be able to understand something in terms of its smaller parts. Right? We have one team within IOHK developing Byron, one team within IOHK developing Gauguin, one team within IOHK developing Shelley, and they are not aware of how this hard fork is going to happen. They can just focus on their part of the problem. Then in the consensus team, my colleagues and I, we can think about the hard fork combinator and how we go from one era to the next. And so we decomposition this into separate problems rather than having to solve everything at once. And since we now have the hard fork combinator, we can go from Byron to Shelley to Gauguin without having to change the hard fork combinator at all, which means that we can support an ever-evolving blockchain very easily. That's all I wanted to talk to you about. So if there are any questions, I will be more than happy to answer them now. Thank you very much.